Okay, let's do an unsteady conservation of mass example here. I am Professor Carey Troy. The problem statement that we have is the following. Water is added to the cylindrical tank below, or to the left, at a constant rate of 4 liters per second. And while it's filling, it's also draining out the bottom here. And we're given some parameters related to the exit area and also the discharge coefficient of that exit. Initially, we are told that the water is 20 centimeters deep in the tank. So the H initially is 20 centimeters. What are we trying to find here? Well, at this instant, the initial instant when this is 20 centimeters, what rate is the free surface rising at or falling at? Secondly, will the water level stabilize, and if so, at what level? And thirdly, how do we expect the water level graph versus time to look for this problem, and how would we actually calculate that graph with numbers if we needed to? So the basic idea here is the conservation of mass, and because we're thinking about water that has a uniform density, we can write that in terms of the conservation of volume. And the conservation of volume for a control volume looks like this. We have that the flow rates in, we only have one flow rate in, minus the flow rate out is equal to the rate of change of volume with respect to time for our control volume. And one thing that we can do for a control volume that has a free surface like the one that we have here, we can rewrite that delta V over delta T using the surface area of the reservoir, which I'll call A sub S, and that's just pi times 0.5 meters squared over 4. Times some delta H. Okay, so basically we can rewrite this over here as AS times dH dt, where dH dt is the rate of change of the surface, and that AS is the surface area here, like that. And then the question is, will the water level ever stabilize? And so whether the water level will go up or down, so whether this dH dt is positive or negative, just depends on whether we have a net inflow or a net outflow for our system. So if the inflow is greater than the outflow, then we would expect a positive dH dt and the water level would increase over time. And if the outflow was greater than the inflow, this left-hand side would be negative, and therefore the rate of change of the free surface would be negative, and this would drain. And what could happen, if there's enough room in the container, is that this system could reach a steady state. Okay? So a steady state effectively means that the inflow minus the outflow is 0. Okay? And if that's true, we have Q in is equal to Q out, and therefore the water level will not change anymore. So dH dt is equal to 0. Okay? And essentially what that means is if you let this thing go over time, the water level will rise up or it may fall down until it's forcing out exactly the right amount of flow, in this case 4 liters per second, that is matching the inflow. Okay? So the water level will basically adjust until you have a balance between the inflow and the outflow, and it will adjust provided it doesn't overflow the container, which is 1 meter tall in this example. Okay, so you'll see how that works. So will the water level ever stabilize, and if so, at what level? So for this one, what we want to do is we want to write out our steady state equation. So I'll do that here. So Q in is equal to Q out. And the Q in is 0.004 meters cubed per second. And the Q out is equal to the discharge coefficient times the outflow area times the square root of 2GH. Okay, and this is at the steady state. Okay? And so all we need to do is plug this in to solve for H. And if we do that, we'll find that the steady state water level is 0.82 meters. And what that tells us is that effectively this container is going to keep rising, the water level is going to keep rising until it reaches a level of 0.82 meters, at which point it will be forcing out 0.004 meters cubed per second. Okay, so basically once the water level gets to this 0.82 meters, it's able to force out the amount of flow that we have for the inflow. 4 liters per second in and 4 liters per second out when the water level is 0.82 meters. And it will just hold constant at that level for as long as we have that inflow going in, okay? So this is the steady state solution, 0.82 meters. So the water level curve, how do we expect the water level to change over time? So what we're going to be graphing here is the water level, h, as a function of time. And again, initially we have 0.2 meters, so this will be in meters. And we have our steady state water level of 0.82. And what we expect is that over time this is going to approach that steady state water level kind of asymptotically. And then at some point it will reach it and just hold constant for all of eternity or until that inflow condition changes, okay? And so the question is, how do we expect the water level to change over time? This is what it looks like, and it will do that. How do we actually calculate that? Well, the starting piece for that is to say, initially, at the same instant where we have 0.2 meters of water, at what rate is the free surface rising or falling, okay? In order to do that, we just go back to our conservation of mass equation, which was that Q in minus Q out is equal to the surface area of the reservoir, the tank, times dH dt. Surface area of the reservoir is known. That's given with the 0.5 meter diameter. The inflow, again, is the 4 liters per second, 0.004 meters cubed per second. And for the Q out, all we're going to do is we are going to say that that's equal to the A out, the outflow area, 0.002 meters squared, times the discharge coefficient, times the square root of 2g, and then we're going to be plugging in that 0.2 meters into that, okay? And if we plug in everything and solve for dH dt, so again, this is the rate at which the free surface is rising or falling. We know it's rising because it's heading toward that 0.82 meters steady state depth. We will get an initial outflow of 0.00198 meters cubed per second, and dHdt, the rate of change of the water depth, is plus 0.010 meters per second. So about 1 centimeter per second is the rate at which this is rising, okay? And so this is the rate of increase right at this instant shown, but what we saw on the last slide is that the rate of change of the free surface elevation actually changes itself with time. And the way to think about that is to think about this water level graph like we have here. We have our initial value of 0.02 meters and our final value of 0.82 meters. And effectively what we just calculated was the slope of this curve. Think about this as some delta H over delta T, our dH dt, at this instant. And as you can see, the slope of the line is changing over time, right? It's getting weaker because the outflow is getting closer to the inflow, and when that happens, we have a slower change of the water depth. So how would we calculate this whole curve? Well, the basic idea is that we're going to take this point here, 0.2, and we're going to use the slope that we just calculated, this dH dt, to nudge our h forward in time to the next time step. So just basically rise over run is going to let us calculate the h at the next time step. And I'm kind of breaking this into a coarse discretization here, but you can use as many points as you want to really resolve that curve, okay? So it will look something like that, and at every time step we will recalculate the dH dt given the new h and the new outflow, and we will bump the solution forward, okay? So what this lends itself to is a spreadsheet approach where we have the first column is time. This is the time that we're trying to calculate our solution at, so 1, 2, 3, etc., and that could be in seconds. What we're looking for is the water depth, A, in meters. We have an initial condition of 0.2 meters. We're going to have an inflow column. The inflow column is going to be 0.004 for all of the times. We're going to have an outflow column, and that's going to be given by our CD times A out times square root of 2GH, and we're going to be grabbing that column over here for our H's for that column. And the last column is essentially our dHdt, and dHdt is Q in minus Q out, so grab those two columns and divide by A sub S, okay? So that last column there, dHdt, Q in minus Q out, and then divide by the surface area of the tank. Now, that's for the first initial condition, and that's basically the example problems that we already solved. And what we have here now is the H for the next time step. So how do we bump this forward? Well, we're going to note here that this new H is equal to the old H, 0.2, plus the dH dt from the previous time step times our delta t. And our delta t is just going to be 1 second, as I've sketched it here. You can use a delta t that's appropriate for your problem. And so for this one, this dH dt is from the previous time step. It's this value over here. And we're going to just fill that all the way down, and we should be able to fill all the columns all the way down, and you can populate this spreadsheet. So you may want to try that in Excel or Google Spreadsheets. And if you do that, you get something that looks like this. So the time column, I've used intervals of seconds. You can see the water level is slowly increasing over time. Inflow is not changing. The outflow is slowly increasing over time because we have more water to drive out the flow. And the dHdt is slowly going down, right? We're sort of asymptoting toward that steady state. And if you run this calculation all the way down to about 800 seconds, you see that we get this steady state water level that we calculated before. You have inflow matching outflow, right? That's basically the definition of the steady state. And the rate of change of the free surface is basically 0, okay? So you may want to try this out, and you should be able to replicate these numbers with the problem that we have here, okay? And the solution, if you graph that H column versus time, looks like this. And again, basically what we said, right? The asymptotic value is this 0.82 meters. The initial condition is 0.2. And over time, it's slowly reaching that steady state water level, okay? So you should be able to make this graph. And you can see that it takes place over, I don't know, 400 or 600 or 800 seconds, depending on how strict you want to be in terms of reaching that steady state. So that's it for the example. Hopefully this has been helpful, and I wish you good luck solving problems.